everyone. And now there will be a 2-hour mathematical introduction on the MAG forward problem. And there will be a little break in 1 hour. So first, we thank Professor Carsten Wolters for accepting our invitation. And Professor Wolters of the Institute of Biomagnetism and Biosignal Analysis of University of Münster has been working for years in developing methods to solve the MAG forward problem. And in this talk, we'll provide an overview of the main methods used in the community with a focus on the finite element method. So, well, Professor, are you ready?
Thank you very much, Lisa. Okay. So yes. I try to share my screen.
Perfect.
Do you see it?
Yes, we see it.
Okay, so it's the longest talk on a conference I have ever given. So I needed more slides, and therefore I will directly admit that I have stolen some slides from Maria Carla Piastra. So you see it in the layout of my slides. So the green ones are from Maria Carla, and since she is with us today, if my karaoke is not good, Maria Carla, please interfere and improve it. So I first of all would like to generally introduce you to the forward problem, and let's say my talk will not only be about EEG and MEG, but let's say you could extrapolate it even to transcranial electric stimulation and transcranial magnetic stimulation, because due to Helmholtz reciprocity, it is closely related to each other. And if we on the EEG MEG side show advantages of certain methodologies due to Helmholtz reciprocity, it can also be extrapolated to the transcranial stimulation parts. I see many let's say things on my screen that people are leaving and coming and so on. I don't know if Annalisa, if you have any chance to stop that, it might help me, because it's really confusing.
Okay, sure, I'll do.
Thanks a lot if it works. Otherwise, I have to accept that. So let's say generally, I would like to introduce you to forward problems in bioelectromagnetism. That is possibly the best title for my talk. So first of all, electroencephalography and magnetoencephalography are techniques used to investigate brain activity with a unique time resolution. On the transcranial stimulation side, TES and TMS are techniques that are used to stimulate the brain. And I think using those methodologies all together is very instructive, because on the one hand, you could try to localize activity from the measured EEG and MEG. And on the other side, you might try to stimulate those focused areas. And if it works, you even have a better impression that the localization was correct and that the stimulation also works. And since stimulation goes more and more focal, the combination of those methodologies makes sense, and the mathematics behind are very similar, because everything is coupled by Maxwell's equations. So the EEG measures the electric potentials, and Lino Nobile presented very well this morning how the EEG is used in epilepsy. And in Münster, we are mainly trying to combine EEG and MEG in the localization of epileptic activity. So we have a large European project that is just starting. I will come to it later on my last slide. Advertise this project where we combine modalities. We do not only combine EEG and MEG, but we also try to combine on the stimulation side methodologies. The MEG measures the magnetic field or the magnetic flux. And it's very interesting because EEG and MEG have complementary information. It's very interesting to combine them. But as we will see, the volume conduction for both modalities is quite different. MEG is much less sensitive to volume conduction than it is EEG, especially to compartments like the skull. And the EEG is the most sensitive to the human skull compartment because it's so low, it has such a low conductance. But the MEG doesn't care at all because the volume currents have such a small, they are so far away from the primary sources and they have such a small amplitude that the MEG is mainly not registering the skull currents. And furthermore, most of them are radially oriented so that MEG can in any case not see them. So this is why EEG and MEG are very different in their sensitivity profiles. And also the combination of EEG and stereo EEG in Lino Nobile's talk, if we try to combine modalities like SEEG and EEG or EEG and MEG, it might be important to have good forward modeling methodologies. It might be especially important to have good forward modeling methodologies. And in especially those multimodal approaches, it might not be sufficient to use a sphere because the sphere is possibly not accurate enough as a volume conduction model, especially for the combination of modalities. So all these pop-ups on my screen are continuing with people leaving and coming.
Yes, I know we are trying to fix the problem.
Yeah, I try to ignore it and to always click it away.
Sure. I'm sorry. I try to solve fast.
Yeah, okay, thank you very much. So I said already that MEG and EEG signals differ and carry complementary information. So for example, Lino Nobile showed us one data set where in the EEG we could not see epileptic activity or interatrial spike activity, while in the stereo EEG it was well visible. And that might be, the underlying source might be more tangentially oriented, and tangential sources, the EEG is not the most sensitive to it because tangential means the poles are quite far away that we can measure in the EEG. So the poles have to travel quite long distances to be visible from the outside of the volume conductor. So they might disappear in the overall noise of the EEG, while the MEG is especially sensitive to those tangential aspects. And since we have long sulci going deep into the brain, we have large cortical areas that are very tangential, so where sources have more tangential orientation. Maria Carla Piastra will show that in her talk this afternoon, where MEG is more sensitive than EEG and the other way around. While the EEG is much stronger for all sources that have the radial orientation, so the gyral crown and sulcal valley sources. So MEG and EEG are complementary. They have different sensitivities with regard to volume conduction, and they have also different sensitivities with regard to source orientations. And if we combine them, we might profit from this complementary information. Source reconstruction is getting more and more important in many applications. And nowadays, even modalities are combined. And so source reconstruction is done by combined SEEG and EEG or combined EEG and MEG, not only to localize epileptic activity, but in general in brain research. Combined EEG and MEG, as I said, has complementary information and might provide source reconstructions that are more accurate and not only in pre-surgical epilepsy diagnosis, depending on the case, surely. Yeah, so they are colleagues, and I do not want to make the claim that combining EEG and MEG always outperforms single modality localizations. What I would like to say is that it makes sense to check EEG source analysis as a single modality, to compare it with MEG source analysis as a single modality, and then to also combine both modalities and try combined localization. That makes sense. And the comparison of those different, of those three source analysis results might be very instructive. Okay, what is source reconstruction? So source reconstruction, first of all, has a forward. We have to solve a forward problem for EEG and MEG. So solving the EEG forward problem means solving a partial differential equation. And solving the MEG forward problem, first of all, needs the electric potential, and it consists then in solving an integration problem. So we have, on the one hand, to solve a partial differential equation, and on the other hand, it's an integration problem for the MEG that we have to solve. This is the basic quasi-static equation for the electric potential that can be derived from Maxwell's equations in the low frequency regime. And there are only few people that claim that it might not be sufficient to use the quasi-static approach, but in EEG and MEG source analysis, most colleagues still rely on this quasi-static equation. And what we see here is the sigma is the conductivity of the different head tissues, and we have quite different conductivities for different head compartments. Like the skull has very low conductivity, the CSF has very high conductivity, cerebrospinal fluid. There is anisotropy in the white matter, for example. So measurements have shown that in a cat cortex, the conductivity along the fibers of the white matter structure is about 9 times higher than perpendicular to the white matter fiber structures. So it's rather complicated volume conductor with a lot of inhomogeneity and anisotropy. And the question is, we do not know sigma exactly. We need models or measurement modalities to measure those conductivities individually. So therefore, there are also different numerical methods, and I will, let's say, discuss a little bit homogenization and boundary element methods and finite element methods. It always has to be seen in the context of what do we know about the conductivities. Does it make sense to throw in many unknowns, or does it not make sense? So this is the most difficult problem possibly in solving the forward problem in EEG and MEG. To find the right balance between homogenization on the one hand, so avoiding an overfitting, and on the other hand, to really model a human head. And the human head is inhomogeneous and anisotropic, there's no question. Most often the sources in our area are modeled as very extremely focal things, mathematical point dipole. So JP is modeled as a mathematical point dipole with a moment m. So the m is a vector, it has a certain position. The position of this vector is at r0, and it has infinite amplitude at that position, and it is 0 everywhere else. This is what the Dirac delta distribution is saying here. So this is surely an overly focal modeling that is not realistic, because in reality we have long apical dendrites that have, let's say, the lower branch of the tree of these dendrites and the upper branch, they are about 2 millimeters away from each other, and it might more be like a negative monopolar cloud in the upper branch and a positive monopolar cloud in the lower branch than really at one point a mathematical point dipole. This in fact causes a lot of trouble, because if we really make it as focal as it is modeled here, and that has a certain history, I think the only reasoning is that it approximates reasonably well a quite focal activity in the cortical sheet, and analytical solutions can be derived for mathematical point dipoles. So this is why still nowadays we use this quite overly focal source model. Yeah, I said this already, and so for the differential equation for the electric potential U, it's elliptic differential equation of second order with Neumann boundary conditions. So there's no current flowing out of the human head. The current that is flowing out in the neck area is ignored because it's so far away already from the brain. And for this equation, Jan de Munk has derived in his work, and also other authors have derived in their work, analytical solutions. They are not fully analytical. Let's say for certain models, you can even produce really analytical solutions, but in Jan de Munk's derivations, he uses series expansion formulas, and they go to infinity. So you have to cut those series expansions at a certain point so that these solutions are quasi-analytical. But let's say if you, depending on the methodology, if you use the first 30 terms of that series, you are accurate up to 10 to minus 8. So we could call it also an analytical solution compared to the numerics. And these analytical solutions are existing in multi-layer sphere models. So most often mathematicians that develop methodologies for the forward problem in EEG, in a first step, they validate their software against these analytical solutions. And that should also be the first step in developing a code before going to more realistic volume conductor models and then even to applications. So in my talk, I will also use the analytical solutions from Jan de Munk very frequently, because we are measuring errors of different numerical approaches, and we most often do that in a first step in multi-layer sphere models against these analytical or quasi-analytical solutions. Okay, the MEG forward problem is then to compute numerically the B field using Biot-Savart's law. In this formula, we have the current density and the overall current density, and this is possibly unique for bioelectromagnetism, that the current density is divided into a primary and additive current density of the impressed current, so the primary current density, JP, and the current density of the secondary flux currents. So the secondary flux currents are depending on the electric potential and on the volume conduction aspects. And those two are divided in the overall current density that is used for the Biot-Savart law. In physics books, you do not, let's say, it has to be a bioelectromagnetism physics book where this division is done. Normally, let's say, you only find these formulas with the full current density. So if we have a point dipole, a mathematical point dipole with a Dirac distribution, then the integration of the primary current density is simple, and we just get for this part an analytical formula for the B field, and then only the secondary flux has to be integrated over the whole volume conductor, so the whole human head, and that is what has to be done numerically. So first we have to compute the electric potential, and then if we know it, we have to compute the derivation, the gradient of the electric potential, have to multiply it with the conductivity, and then we are able to integrate over all secondary currents that also add up to the overall B field. So we have to compute the primary magnetic field and the secondary magnetic field, and numerically the secondary magnetic field is the more complicated part, the integration part. Okay, so JS is, as I said already, is the part of the MEG forward solution that depends on the electric potential that has to be computed by solving the EEG forward solution, so the partial differential equation that I showed before. In fact, MEGs are not measuring the magnetic flux, the magnetic field or magnetic induction B, but the MEG measures at sensors which have a phase or a surface S. It measures the integration of this magnetic field, which by Stokes' law can also be expressed as a line integral over the outer contour of that sensor over the magnetic vector potential. So in this equations, B is the magnetic field or magnetic induction, A is the magnetic vector potential, and the law of Stokes has been used in this formula. S is the phase of the sensor and C is the contour of the coil. And for the MEG forward solution in, let's say, simplified volume conductor models, like for example, one sphere or multiple spheres or radial and tangential anisotropic spheres, that is all the same. All these conductivity inhomogeneities were shown by Ilmoniemi and Savas to have no effect on the MEG. And analytical solutions show this, so that, let's say, if the head would be an ideal sphere and we would have radial anisotropies in the inner compartment, those anisotropies would not have any effect on the magnetic field. So the MEG, let's say, from these studies can be pointed out to be much less sensitive to many of those conductivity inhomogeneities and anisotropies that we have in a real head. However, in the real head, nothing is really spherically symmetric, so all these assumptions are no longer valid, and anisotropies have an effect, and skull conductivity has an effect, but the effects are still low compared to the EEG. Okay, so once the potential distribution U is computed, this has to be done by solving a partial differential equation. We can integrate the secondary currents that result from this electric potential and the conductivity distribution in order to compute the secondary part of the B field, and then we can use these formulas to compute the magnetic flux and compare it with what our MEG has been measuring. So what do we need for the forward problem? We need a head model. So we need electrical features, geometrical features, and in validation studies, we most often have a simple head model like multi-layer sphere model as shown here. So this multi-layer sphere model has 4 compartments: the brain compartment in the middle, the green compartment, the yellow, and the skin compartment. By the way, do you see if I move my pointer here? Do you see this?
Yes, we see.
Okay, thank you. And then surely, let's say that would be the first step of a validation, and then we have to go to a real head. And as we see, the real head is, let's say, not too far from multi-layer spheres, but still quite far from multi-layer spheres. So therefore, we need numerical mathematics for the realistic geometry. Then we need a sensor model. I will not speak about sensor models. I will assume point electrodes and point sensors in my talk, but we have also developed a complete electrode modeling in order to better take into account surface and impedance and shunting currents at the electrodes. So there are more complicated electrode models. From our experience, if we model the EEG with a point electrode model or with a complete electrode model, it makes a difference in specific situations. For example, in baby heads where we have many electrodes and only a small surface, there it might make a difference. In adult heads, we only found smaller differences between those sensor models. Also for the MEG, if we use single integration formulas for each magnetometer, or if we use multiple integration points. For very eccentric sources and for certain sensors, it might make a small difference, but it is really a small difference of some few percent. So very often a single integration point in the middle of a coil and multiplying this with the sensor phase is doing a reasonably good job. The source model is more complicated because, let's say, nobody can tell us what the best source model is. We know that it is not as focal as the mathematical point dipole, definitely not. But it is difficult to define the atomic particle of our inverse problem that is best, let's say, the best one for source analysis. So therefore, still, most often we rely on the most focal one, which is the mathematical point dipole, and let the inverse problem do the rest. However, let's say, often it leads to over-modeling then on the forward modeling side, because people try to really get that singularity as accurate as possible, which is then also important if we define it as a mathematical point dipole. But in reality, it's really not. There's not a single such focal source in the brain. So it might be that we can relax it, regularize it a little bit to have less problems on the numerical side. And I will tell you a little bit about source modeling in FEM, where it can be done quite easily. There's a vast spectrum of numerical approaches for solving the differential equation. I started with boundary element methods and later on joined an engineering group in Aachen, where I started, let's say, with the finite element method. And there are also other methods like finite volume methods, finite difference methods. Let's say I will discuss that a little bit, but the focus of my talk is on the finite element method. And the reasoning why we use finite element methods is possibly presented in the guideline study from Johannes in 2014. So Johannes has used a 6-compartment anisotropic head model with high resolution. So that is our reference, a real head model with 6 compartments. The compartments brain gray matter, brain white matter. White matter has been modeled anisotropic. The cerebrospinal fluid, isotropic, skin and skull, isotropic, and in the skull, we have even distinguished the compacta and the spongiosa in this 6-compartment model. And the high resolution model had nearly 2.2 million degrees of freedom. So let's say lots of computational work. That is our reference head model. And now we compare to that reference head model, to the forward computations in the reference head model, we compared simplifications. So the first simplification might be a model that has the same shape, so 6 compartments, also trying to model white matter anisotropic, but with much less degrees of freedom in order to reduce the computational effort. This model was let's say about 1 million degrees of freedom has then also been used to go down with, or to go up with the homogenization. So let's say what is mostly used in our community in source analysis is still nowadays the 3-compartment model, where brain, skin, and skull are used as the 3 compartments. And it is assumed, in order, let's say, with the goal to homogenize well, it is assumed to homogenize over gray matter, white matter, CSF to make it one parameter. The one parameter is then the brain conductivity, and there's only one compartment. Same is done in the skull compartment. There's no distinction between spongiosa and compacta. It is assumed to be one compartment, one isotropic compartment. And we wanted to see how different the forward approaches are in those models. So we have also 4-compartment and 5-compartment and 6-compartment. So we go up with the compartments, and this table here shows what exactly has been homogenized and what not. And it has been shown in in Johannes' study that realistic modeling of the volume conductor has a strong effect on both EEG and also, surprisingly, let's say at least some of the compartments, especially the inner compartments, so CSF, gray matter, white matter, anisotropy, has also an effect on the MEG, especially the secondary fluxes, the secondary currents that are quite close to the primary current. In that area where you have the CSF and the gray matter and the white matter anisotropy, these currents might be quite different from a fully homogenized, let's say, symmetrical arrangement in the environment of the primary sources compared to a realistic head where you have these anisotropies and the conductivity jumps close to the sources. So numerical inaccuracies have been shown to be negligible compared to the modeling effect. So what is very often done by forward modeling people like me also, oh, if we get 1 or 2% more in this approach, then we publish this approach and this approach is the overall winner. Let's say compared to what we need in brain research, it is really negligible, these 1 or 2% differences. Nobody cares. It is more important how we best homogenize the volume conductor model, or that we do not homogenize if we can't. If the effect, the real effect of these inhomogeneities is just too big, then we have to try to model it. And Johannes' study in this guideline clearly showed that the modeling errors, the modeling effects of the different compartments is much, much bigger than these few percentages in numerical accuracy that can be achieved in a multi-layer sphere model, comparing this approach with that approach. So in the guideline, Johannes claimed that, let's say, we have to start first of all, in this study, we did not investigate the skull so much. It was not in the foreground, but here I would like to say that modeling the skull is surely by far the most important compartment for the EEG modality. It smears out the potential distribution. Skull conductivity is very individual and let's say it would be important, or to make an extreme example, if we have a baby, the skull is not even closed. There are fontanelles and sutures, and the skull plates have an about 10 times or 80 times higher conductivity than a skull in an adult or in an old subject. So the conductivity will be definitely very much depending on the age of the subject. And we have also recently shown that we can work out a dependence of the conductivity on the age, also in the middle age class, let's say the subjects and patients that we normally measure in our institute from, let's say, 20 years to 50 years. Even in this age class, we could work out a significant dependence on age and also on skull thickness. So let's say skull is the most important. That should be the first point in a good guideline. It was not investigated in Johannes' paper, but only for the EEG, for the MEG, not at all. The CSF is then the next compartment, and Maria Carla will show the effect of the CSF if we ignore it on the EEG side. On the EEG side, it has a very significant effect, and also on the MEG it has an effect, because it is so highly conductive and it is so close to the sources. Gray and white matter distinction also seem to be important from Johannes' work. There's white matter anisotropy that can play a role. In many applications it will not. In specific applications like, for example, SEEG, EEG combinations, it will definitely make a big difference, because the closer the sensors come to the sources, the more important all these inhomogeneities will get. We found rather smaller sensitivity of EEG and MEG not at all, smaller sensitivity of EEG to the distinction of skull compacta and spongiosa. However, if T2 images are available, it definitely makes sense, because the spongiosa is about 3.5 times higher conductive than the compacta. it might make sense to distinguish those two in the head model. But most importantly, the compartments close to the source that are, let's say, fully ignored in a 3-compartment head model that is most often used in our source analysis community, those 2 compartments seem to make a difference, especially to source orientation estimations, source magnitudes, and possibly also to source location, even if that is a little bit less affected. Okay, so let's come to more to the mathematics. That was, let's say, first of all, I tried to point out what I think from our experience is very important and what is less important. So 2% for me is, I don't care. Then I take the method that is more flexible. If it is 10% or 20%, then it gets, let's say, significant, and it might have an effect on the clinical diagnosis even. So what has been developed over the last, let's say, since computers are existing, is the boundary element method, and that was also my starting approach. I studied mathematics and was a minor in medicine in Aachen, and I had 1 year abroad in Lyon in France and worked with François Perrin, and some of you might still know François. They developed BEM and FEM methods in the INSEAM lab in Lyon at that time, and my task was to implement boundary element methods, and I compared it also with FEM methods. So I had first contacts, but I mainly worked on BEM methods. And when I came back to Aachen, I found an engineering group around a neurologist, Helmut Buchner. And these engineers in Aachen, they are only using finite element methods because, let's say, they build simulations for motors in cars. And let's say the FEM is just very flexible. And I learned a lot about applications of FEM methods with the engineers. And since then, I'm mainly focusing on FEM methods, even if I'm also very interested in the mathematics of BEM. And I think there are also BEM methods nowadays that can go up even with the compartments. They can even model a CSF compartment. Very often, they do not really model the full, let's say, detailed CSF compartment, but they smooth it a little bit so that the not too many surface nodes are introduced. That is important, let's say, that the computational effort is not exploding. So let's say the more inhomogeneity is added, the more arguments are on the finite element side compared to the BEM side. I think that is a statement that I could give. There's also finite volume method and finite different method, which is not too different from the FEM. So therefore, let's say I focus on FEM because we have also, let's say, geometrically advantages if we use FEM approaches. In the FEM area, you will learn today about, or you have heard already about continuous Galerkin. So that is the standard finite element approach where the electric potential is kept continuous. So the assumption is, okay, and that makes sense physically, the potential should not have jumps. Yeah, the potential should be a continuous function. And the continuous Galerkin FEM approach keeps the potential continuous. But due to the jumps in the conductivity, a result is that the current is no longer fully continuous. There might be jumps, small numerical jumps in the current from one element to the next, because the gradient of U is not fully compensating the conductivity jump. So the conservation of charge is not fully fulfilled. And therefore, even if it sounds strange to a physicist, it might make sense to also check discontinuous Galerkin approaches, where on the one hand, we on free will, let the potential jump. So that is quite unphysical. From one element to the next, the potential could jump. But we can prove that the conservation of charge is fulfilled also in the discrete sense. So the current is then kept continuous from one element to the next. And there are scenarios where that makes sense and where the DG FEM might be advantageous compared to the CG. And I will show you such situations today. I will also put a focus, especially in my second part, on unfitted FEM methods, more on CAD-FEM than on UDG, because CAD-FEM is computationally more efficient. But all these unfitted methods, let's say, are practically also very interesting for our research domain, so that we try to push these methods, because mesh generation and everything is simpler. We only need level set informations, so that might, let's say, push the finite element computations that are very often seen to be practically too difficult. If we have to model 6 compartments, let's say, it might be too difficult work, too tedious work to set up the model underneath for a group of subjects, for example, which is one of the main arguments why people start using spheres or BEM approaches, because that is just simpler. If I go down with the compartment, it's easier. If I have only 3 compartments, I have less work than if I have to segment 6 compartments. That's surely true. And I will also, if there's time, I will also speak about mixed FEM approaches. And mixed FEM, we can keep potential and current continuous over the volume conductor. That is, let's say, the interest in, or the interesting aspect in the mixed FEM approach. There are also papers for immersed FEM, and I think the next slide shows the underlying paper. So the immersed FEM has been published by the colleagues at INRIA in Nice, around Maureen Clerc and Theo Papadopoulou. That is also very close to, let's say, our unfitted FEM approaches. So let's say I will mainly focus then on unfitted FEM in this area. Okay, so what I want to present in the first part, let's say still the slides of Maria Carla, the continuous Galerkin, the discontinuous Galerkin, and the UDG methods, and let's say how they are different, how they are similar, and what we might be able to do with those. So in Galerkin methods, what we first have is a strong formulation. From the strong formulation, we formulate the problem in a weak variational formulation, or we derive a weak formulation from it. And then we discretize this weak formulation and solve it with linear algebra possibilities. So let's say solutions of large linear equation systems. So the strong formulation is our potential equation. So here it has been simplified. So Laplace of the potential and the right-hand side. So what is the potential would be the strong formulation. And then we multiply this equation with the test function on the left and on the right-hand side. And we integrate it over the volume conductor model. And then we ask ourselves, okay, what is the solution for that weak formulation? On the left-hand side, partial integration is used. So the divergence of the gradient of u, the divergence is put over to the test function. So in fact, there has to be a minus, Maria Carla. So there it is minus the integral over the gradient of u times gradient v. And on the right-hand side, we have, let's say, what is shown already here. Let's say, and this is only the case if the surface integral can be ignored. For example, if we have a test function from h0, or if u goes down to 0 at the boundary. And from this problem, from the weak formulation, we can then formulate bilinear form. So the bilinear form in this case would be simply this operator here. And the left-hand side functional would be this functional in VH. So let's say here, from here on, we use a finite dimensional subspace of the function space V. And this finite dimensional the use of this finite dimensional subspace with certain basis functions then allows us discretize this problem and to formulate a linear equation system that is then solved using, for example, iterative solver methods, multigrid and similar approaches. So that is, let's say, the way that the finite element methods take and many other methods take from the strong formulation of the problem up to the equation system that has been derived from it. So in the standard Lagrange type methods, we have the degrees of freedom at the nodes. So that would be the continuous Galerkin approach on the FEM side, where the degrees of freedom are at the nodes. So the potential is kept constant, continuous from one element to the next due to that choice of node-based basis functions. There might also be, for example, L2 conforming elements. If we have just one degree of freedom in the cell, then let's say the potential is kept constant in that element, and it might be a different constant in the neighboring element. So in fact, the potential then makes a jump from one to the next element. And that would be, for example, an approach that could be used in discontinuous Galerkin, where we do not assume that the potential is constant. We let it jump in order to take care of the jumps in the conductivity structure of the volume conductor model. So first of all, the Lagrange type is the continuous Galerkin, and the L2 conforming is then a discontinuous Galerkin approach. So let's start with the standard continuous Galerkin for EEG and MEG. So the goal is here to evaluate the electric potential U. The big problem what we have, if we really assume that JP is a mathematical point dipole, then as a mathematician we have to know, okay, a delta Dirac distribution, in which function space is it? It is in H minus 3/2 plus epsilon, in H 3/2 plus epsilon, and the divergence of it is in H 5/2 plus epsilon. So it is extremely singular, and we have a real problem. And in fact, mathematicians would say, oh, then we have a real problem with U, because it cannot be in H1, because this is just too singular here on the right-hand side. So somehow our forward equation has a problem, and we have to get rid of that problem. And one mathematical, let's say, one way to get rid of that problem is to use the singularity, the subtraction approach. So we subtract the singularity out of that equation by splitting the potential into a potential of the singularity itself. U infinity would then be a potential distribution of a mathematical point dipole at a certain position in the volume conductor. And U infinity is a solution that is created for an infinitely extended volume conductor model with homogeneous conductivity. And the homogeneous conductivity is the sigma infinity conductivity. So there is no inhomogeneity of conductivity in that, let's say, infinitely extended volume conductor. For this potential distribution U infinity, we have analytical solutions. They also have singularities due to the very singular source, but it can be computed analytically. And then we can extract this analytical potential from the equation, and we can derive a partial differential equation in the correction potential that can then be solved numerically. And if we do that, we end up in the weak formulation with this formulation. So we have on the left-hand side only the correction potential and the test function from a test function space. And on the right-hand side, we have now, let's say, everything that can be computed, that is known because we know analytical solutions for U infinity. So we can compute this volume integral and we can compute this surface integral. And that has been published in 2009 by Drexler et al. So from our group, we have shown in this paper that we have to integrate reasonably well this volume integral, let's say up to order 2 at least, quadrature formulas to have an accurate forward solution if we use linear test functions. So the solution can be proven that it exists and that it is unique using Lex-Milgram and such constructs. Yeah, okay, so Maria Carla derived the weak form on the smartboard. I will not do that here. So if we have then the solution of that problem, so we have computed analytically the U infinity and we have computed numerically the U correction potential, we can add it, and then we have the overall, the total potential in the volume conductor model. And then we could go over to the MEG problem, where, let's say, this is then just an analytical expression that we have to compute, and the secondary fluxes we have to integrate over a sigma gradient of the electric potential that has been computed. So this is then the next integration problem that we have. So we have to integrate over sigma gradient U, and we have to do that for the infinity potential and the singularity potential and the correction potential. So that would be what we do if we use a Lagrange FEM approach, a continuous Galerkin FEM approach, and we use the subtraction approach for the source. Let's say under the assumption that it is really a mathematical point dipole, a very, very singular source model on the right-hand side. So in the discontinuous Galerkin, let's say a motivation came from this, let's say from looking at the segmentation of the human skull. And if we go in this area here, and this is really happening a lot in practical applications. So let's say we had that problem. We used Lagrange approaches, FEM approaches, on volume conductors that had these kind of skull segmentations. So the inner skull compartment might, for example, be the yellow one. So that might be the inner skull, and the outer skull might be this blue or even the red one, which would be even worse. If it is the red one, then in certain areas, the skull is disappearing. Yeah, it is only present by one point. This voxel is inside the skull, this voxel is inside the skull. This would be brain, and this would be skin. So these situations, if we then use finite element approaches, Lagrangian finite element approaches with hexahedral meshes, and we start producing meshes, regular hexahedral meshes from such a segmentation, we end up with this problem. So we have the skin compartment, which is C2 here, and the very low conducting skull compartment C0, and we have the brain compartment, or the CSF, let's say, compartment. And if we now have these 4 elements here, in reality, it would be then that what could happen, what could come out of such a segmentation and such a model generation could be that this is a point that is used as a degree of freedom in a Lagrangian FEM approach. And this element would be skull, this would be skull, but this would already be skin, and this would be CSF. So currents that come from here, they go through the CSF compartments, through the CSF hexahedra, they come to that point and they might leak out to the skin compartment. And that is exactly what we call skull leakage. And in these scenarios, it is very interesting to look at discontinuous Galerkin approaches. So that is our motivation. So in discontinuous Galerkin, the conservation of charge is taken care of. So let's say in the subtraction approach, we can show that the conservation of charge has on the left-hand side the J correction term, which is sigma gradient U correction, and on the right-hand side, the F correction part is this term here. So it can be derived. It is derived in the paper of Engwer et al. That I mentioned. And we can prove that even in the discrete sense, the discontinuous Galerkin approach takes care of that conservation of charge. So in fact, if there is no source, this term is 0, and then all the currents that penetrate an element that go in or go out, the sum, the integral over all of those has to be 0. If there is a source in that element, then let's say it has to be taken care of. So let's say if there's a monopole inside, current has to flow out of that element, and this current has to be identical over the surface as has been produced on the right-hand side. So that is the conservation of charge. And it can be proven that in the discontinuous Galerkin, it is taken care of, even in the discrete sense. So, but in general, a conforming discretization does not guarantee this property. So what is done in the discontinuous Galerkin is that we also use a triangulation of a domain. So we have a finite set of disjoint open sets. So that might be, for example, a hexahedral, regular hexahedral head model. The H is here the mesh size. So let's say if we use regular hexahedra, it's always identical, 1 millimeter or 2 millimeter. So 2 millimeter would be coarser, 1 would be already, let's say, 4 million unknowns or something like this. In discontinuous Galerkin, we then look at broken polynomial spaces. So we have functions V from L2, where there might be jumps from one element to the next. So inside one element, it is somehow a polynomial, but in the other element, it might be another polynomial, or let's say the constants might be just different in two neighboring elements. So the potential could make jumps. It is only assumed that it is an L2 function here. So therefore, at the boundaries, we have certain operators, and what is used in the formulas in discontinuous Galerkin theory of Di Pietro, for example, that is an important paper for these aspects from 2008, is jump and average operators. And here we see the jump of the potential U that is let's say determined by the potential U in the, so we have element E and element F side by side, and there's a phase between those two elements. So we have a potential in the element E, and we have a potential in the element F. And if this potential is multiplied by the normal at that phase, and the normal from the point of view of the E element is pointing in that direction, and the normal from the point of view F element in the other direction. So in fact, the jump operator of the potential is a vector valued, and it is computed on this way. And there's also the average operator, and the average operators is let's say computed on this way. So we take the conductivities between those two elements. The F element has the conductivity sigma F, and the E element has the conductivity sigma E. And then the average operator calculates this, is defined in that way. So then there are different possibilities, and we are on the DG side, we are mainly focusing on the symmetric interior penalty Galerkin approach, ZIPG. sometimes a weighted is also put in the middle between those two words. So SWIP G might also in the literature might be found. So here we have to compute the correction potential in that different space. And on the left-hand side and on the right-hand side, it's now getting more complicated. So we have more terms. And why do we have more terms? Mainly, or let's say I will show you what it is about. So in the Lagrangian approach, we only had this operator, which was this bilinear form. And on the right-hand side, we had the integral over the head domain and the integral over the surface of the U infinity singularity potential. Now we have further terms. And the main point, because we have further terms, is that since the potential can now jump, we have to integrate, let's say, if we use partial integration, we always have these additional surface potentials that we have to calculate. So the gamma int is the whole interior skeleton. This is called the skeleton of the head model, where surface integrals have to be additionally computed. So it's a lot of additional integration over surface elements. And let's say one of these terms is stemming from that, from the surface integrals that additionally come in when using partial integration. But they are also, in order to gain a joint consistency, a second term has to be included, or is included. That has been shown by Di Pietro in 2008, that this term is needed for a joint consistency. And then there's also a penalty, and the penalty is mainly used, let's say, to guarantee coercivity of the bilinear form. And as we see, the penalty is punishing if jumps are getting too big. That is, on the one hand, happening. That's, let's say, what a penalty is doing. If the jump gets very big, this penalty is getting very big. So let's say we try to keep the jumps in reasonable size. On the other hand, the differences in conductivities are taken care of in that area where the potential might jump. And also the shape of the elements is taken care of. So that also weights how much the penalty is given strength. And for example, let's say if we have a very small element, it does not happen in regular hexahedra, but if we have tetrahedral situations, it might be that we have a very small tetrahedron and a very big tetrahedron at the side. Then these terms of the penalty are weighted quite strongly, so that it is punished a lot, that potentials jump from very small to very big elements. So this, let's say, these are the differences in the formulations. Finally, we can also derive an equation system out of it that we have to solve with efficient solver methods. And it, let's say, theoretically, it can be proven that...
Sorry, Carsten?
Yeah?
If for you it's okay, we may have a break, or as you want to.
Yeah. I did not check the clock, so let's say whenever there's time for the break, I think it is now 1 hour and 10.
Yes.
Okay, so sorry.
No, if for you it's okay, as you prefer.
Yeah, sure. We can make a break and
in 10 minutes so we can start again.
Yes.
Okay. Thanks.
So should we just make a break or allow questions, or what do you?
Yes, also, if there is some question in the middle time. Thanks for, it's very interesting.
Does it work?
Yes, we see.
Should I just go on, or?
I think yes, we can restart.
And I can go on up to 1 o'clock, huh?
Yes.
Or should there be some time remaining for discussion, or how would you like to have it?
No, I think also we can do some questions after.
After
So,
1 o'clock.
Yes, if you finish at 1, we can take some minutes from the lunch for the questions.
I'm very flexible, so I have lots of sites and I can, let's say, focus more on this or that, and I can make it shorter. So depending on the best, what you would like to have the best.
Yes, also as is best for you.
Yeah. So always
Feel free.
interfere if, let's say, with regard to timing. Yeah. If
Okay.
okay, so let's go
Okay.
on. So for the discontinuous Galerkin, oh, I have to make this smaller here. Okay. So what we can show is that if the eta of the penalty term is only sufficiently large, and let's say after some tuning, we now have a parameter that we always use in these simulations, the SWIP-G discretization has a unique solution, and it is also consistent with the strong problem. And especially if we define the correction and the left-hand side and the right-hand side in this conservation of charge law in this way, then this discretization fulfills a discrete conservation property. Okay, so this can be shown, but what does it mean in practice? So when coming back to that problem, if we have a Lagrangian FEM approach, I said that current could flow through the node without interference of skull conductivity. The current could flow from a CSF compartment into the skin compartment. So it could leak out of the head without being interrupted by a skull compartment at that point here. So that would be surely, that might lead to a significant effect. So we have to examine it. And we saw that it causes trouble in hexahedral models. At a certain point in time, we thought that we cannot really offer hexahedral models to the community due to such aspects, especially when we have thin compartments in babies or in animal models. The first time we had that problem was, in fact, a rabbit model in a cooperation with Jena, where we modeled a rabbit head and where we had lots of these skull leakages. In the DG version, since the flow is continuous over phases, it cannot be that current flows over a node. It has to flow. It gets in contact with the skull compartment because the current has to flow through the phases. So even if there's a direct contact point, the current is flowing through the skull compartment. So the potential is much reduced by the skull. There's a large gradient of the potential in the skull compartment, so that much less current appears in the skin compartment, or the other way around in brain stimulation. Yeah, reciprocally, it's the same. So that, let's say, the DG-FEM alleviates the skull leakage problem in regular hexahedral meshes. And let's say if we have a regular hexahedral mesh, I will come to that point later on. If, let's say, it might be better not to have such models, yeah, then we also do not have that problem. But if we have hexahedral meshes, we might face that situation. For example, here's a model that has been, let's say, that has been shaped in a way that the problem gets significant. Yeah, and the problem gets significant if the skull compartment is very thin. So here we have a lot of these only 1 point scenarios where the skull is only, let's say, consisting of a point, where this point keeps together 2 skull elements. And if now a source is pointing on such a leakage point, and we use a continuous Galerkin FEM approach, then large currents flow to the CSF compartment here. They are so here are the 2 skull elements, and this high amplitude current is then flowing into the skin compartment. There's still very high amplitude, while in the DG-FEM simulation, the amplitude is much reduced. If you look, it has the same scale. So if you look at the color coding, the DG-FEM really reduces a lot these skull leakages. In the SIAM paper, we have evaluated it. Okay, so now Maria Carla is going over to the MEG approach. I think what we should show here, also due to timing, is mainly the results. So first of all, we show results in a 4-compartment head model, sphere model. So we have inner radius 78, the CSF is 2 millimeters thick, the skull compartment is 6 millimeters thick, and the skin compartment is also 6 millimeters thick. We have the very high conductivity of the CSF and the low conductivity of the skull. That is a realistic, let's say, setup for a human head. If we now check for 1 millimeter segmentations, for 2 millimeter segmentations, and for 4 millimeter segmentations, we see that between so on the x-axis we have sources with different eccentricity. That means differently close to the first conductivity jump in the brain compartment. So 0.993 is extremely eccentric source that comes very, very close to the CSF compartment, and it is known that numerical errors explode if a source singularity comes very close to the first conductivity jump. So the numerical errors are larger, and resolution of the model is then getting very important, and that is surely the case for both methods, the CG or the DG FEM. For lower eccentric sources, we see that, okay, in the 1 millimeter case, we hardly see any difference between CG and DG scenarios in this 6 millimeter thick skull model. And also for the higher eccentricities, there's not really a big difference if we have 1 millimeter resolution available. For the 4 millimeter resolution, we already see, especially for the most eccentric sources, that, okay, there is, let's say, a disadvantage of the Lagrangian approach. The topographical errors, RDM, are larger than for the discontinuous Galerkin approach. If we check I think this is a median. So if we check the median, there is already, let's say, a considerable change in median between those two situations, but this is still not extreme. Same for the magnitude error. It gets extremer if we now make the skull thinner. So here the skull has still 4 millimeter thickness, 3 millimeter thickness, 2 millimeter thickness. For 2 millimeter thickness, if we have a model with 2 millimeter resolution, and this is visualized here, so the model has 2 millimeter resolution and the skull is only 2 millimeters thick. So let's say quite a thin skull for a coarse resolution. And if we have such situations, then first of all, the number of leakages is strongly increasing. For the 2 millimeter skull thickness, we have then 10,000 leaking points, and then it is really appearing much stronger in the accuracy results. So we see a significant difference between discontinuous Galerkin and continuous Galerkin approaches for the 2 millimeter resolution models, especially for the most eccentric sources, but also for less eccentric sources. There's always this huge difference between DG and CG simulations. So in fact, let's say if we have thin compartments, especially the human skull, if the human skull is thin in certain areas, and the sources are close to those areas and electrodes are over those areas, then these leakage effects might be visible in hexahedral models. So I would say a big disadvantage of hexahedral models, if we use hexahedra, it has to be definitely 1 millimeter models. 2 millimeters, much too coarse. And we have to be aware that such problems can happen that do not happen if we go for surface-based approaches. If we produce surfaces if we then mesh these surfaces, if the surfaces have a certain distance from each other, if we mesh the surfaces into a triangularized tetrahedral head model, then we do not face those skull leakage problems in FEM approaches. It only happens in these regular hexahedral modeling approaches. But it's very instructive to learn about it, because then we will understand why cut FEM and unfitted FEM approaches might be especially interesting for us, for our community. Okay, so some further results. Let's say I will go over them faster. I will also go, Maria Carla, I will go over the MEG part a little bit faster, because I would like to have enough time for cut FEM and for mixed FEM. So I will mainly only present the main results for the MEG part, and the main result is that MEG is much less affected by skull leakages. So if we have 1 millimeter hexahedral models for the CG or the DG FEM approach, the RDM, the mean RDM errors are quite similar to each other. So both methods perform very well with a mean of 1.5% numerical error, which is negligible, let's say, compared to noise in the data in EEG and MEG and so on. Also, the MAC error is negligible for source eccentricities that are, let's say, about 2 millimeters away from the next conductivity jump. And most importantly, in Maria Carla's investigations here, Maria Carla implemented CG and DG methods into our DuNeuro toolbox and compared or tried to work out if skull leakages might also affect MEG forward computation, but it did not, in fact. And it's also logic, because the MEG is just not affected so much by the volume currents, just only have a certain effect on the overall solution. Most importantly, changes close to the sources make a difference for the MEG, and especially changes of the source model itself make a big difference for the MEG. Less these leakage problems far away from the sources, while it is different for the EEG situation. So that, let's say, we could overall summarize that, first of all, CG or DG makes a difference mainly if we use regular hexahedral head models with coarser resolutions, and we run into that problem that the resolution is not fine enough and we have thin compartments that we would like to model. So that is a dangerous situation for hexahedral head models. On the EEG side, it might have a significant effect, especially if it is about the skull. On the MEG, it does not have. If we want to merge EEG and MEG into a multimodal EEG and MEG simultaneous source analysis, the skull leakages make the effect on the EEG side, so that it would be good to have one and the same numerical method also on the MEG side. So in those situations, we would go for DG FEM in EEG and MEG combinations. But there are better possibilities, let's say, where we do not even run into that problem, because we use level set information and we cut the regular hexahedra in cut FEM approaches, so that the geometry is better taken into account, like in surface-based approaches. So here, let's say we would like to advertise the software. Since about, let's say, when I started, we developed the Symbio code, and the Symbio code is now part of Curry and part of BESA, of the commercial toolboxes. It is also part of Fieldtrip. It has been integrated in Fieldtrip. But it is a software dinosaur, because it still contains Fortran codes that I got from the engineers from Aachen who simulated motors, and it's a very old code. So the computational, let's say, computationally it's very fast, but the software structure is not up to date. So 10 years ago, when Christian Engwer came to Münster, we developed Dune Neuro, which is based on the Dune project. And in Dune Neuro, we have re-implemented the Lagrangian approaches on the EEG and MEG side, and Dune made it possible that we could easily also, or not easily, but we could extend our developments towards more sophisticated FEM approaches. For example, discontinuous Galerkin or CAD-FEM approaches. So we use the features of the Dune toolbox available. And the whole software is now written, or most of the software is now written in C++. It's open source. It can solve partial differential equations, and we offer it. We have now a software paper in revision in +1 that we hope will be accepted soon, so that then also the software description, test scenarios, and test data are available that you could try it yourself. I think it's now a much better organized code, and we are on the way to implement it also in other open source tools like Fieldtrip and Brainstorm to make it really available to the community. We call it Dune Neuro. So that is, let's say, in fact, the logo of our Dune Neuro code that is based on the Dune software. And Maria Carla did a lot of work for embedding the Dune Neuro in Fieldtrip. We now have an NIH project with John Mosher and Richard Leahy, where Takfarinas Medani is embedding Dune Neuro in Brainstorm. And where also head model generation is quasi automatically done, so that, let's say, surface-based or hexahedral approaches can be used to construct head models. Okay, summary: conservative representation of the flux increases the accuracy of DG-FEM in MEG. That is a part I have now jumped over a little bit faster due to time aspects. The DG-FEM and also the CG-FEM have only very low errors of, let's say, 1 or 2% on the MEG side, and also if we have sufficiently fine models on the EEG side, so the numerical errors can be ignored or let's say neglected. Both the CG or the DG-FEM. Skull leakages do not play a role for the MEG, but they play a role for the EEG modality. And thereby, in a combined EEG and MEG, where we would like to have the same forward model for both modalities, for one and the same head model, it might make sense to use DG instead of CG. It is computationally more expensive because most often it has, let's say, depending on the choice, it has more degrees of freedom overall on the DG side. So it's computationally less effective than the CG-FEM. However, let's say if a good computer is doing the job, we don't care, and we, let's say, would motivate people to just compare results. So use the CG, create an inverse source analysis result, use DG, create the same result, and check if there are differences. If there are significant differences, then you might have run into such a skull leakage problem. And then you know that with DG, let's say, the problem will be alleviated. So DG-FEM complements, and in some cases, as for example the skull leakage scenarios, it can outperform a standard CG-FEM in EEG or combined EEG and MEG scenarios. And then Maria Carla also in her paper produced a proof of concept where for a source in a realistic head model, she produced a potential distribution, visualized a potential distribution, and also an MEG forward solution for one and the same source to show that with DG-FEM you can produce dipolar patterns on in the sensor cap that we know as EEG and MEG loss. Okay, the unfitted discontinuous Galerkin in Maria Carla's presentation here was just very short, mainly citation of Andreas Nüssing's paper in IEEE where we presented the method for the first time. the UDG, unfitted discontinuous Galerkin, has good conservative properties, or takes over the good conservative properties of the DG-FEM. It uses also hexahedral meshes, and the meshes can even be coarse because the fine geometry is taken care of by level set surface information that should additionally be available to use these approaches, and then it is able to eliminate geometrical errors. And in my second part of the talk, or a little bit later, I will show how it does it in let's say in more detail. In the UDG obtains the same accuracy in tetrahedral models as DG-FEM. It outperforms DG-FEM in hexahedral models, but it also needs more information on the level sets. And it better controls the computational costs. So CAD-FEM and UDG are methods, unfitted FEM methods, that can be quite effective because we invest the degrees of freedom in a better way. So adaptive FEM methodology might also be pushed on this way because we can invest the degrees of freedom where they are really needed. For example, a little bit finer meshes in the source areas, a little bit finer meshes in areas of the skull or the skin where sensors are, or where the potential just falls off significantly. So these methods are, let's say, very flexible for this kind of forward modeling. And that is visualized here in this figure, where we see on the one hand a surface-based tetrahedralized FEM approach of the FEM model of the 4-compartment sphere model. And on the right-hand side, we see a UDG on an unfitted FEM approach, where it already gets obvious that we have a regular mesh structure, and in important parts of the volume conductor, more work is done in different directions that I will explain a little bit later on in my talk. So let's say, if we visualize it in a fine area, it might be that UDG uses a coarse, let's say, element in the inside of the skull, and the next element would already be an element that cuts 3 different compartments, and then unfitted FEM takes care. So it does not only segment this whole hexahedral element to belong to only one compartment. That caused the trouble with the skull leakage problems, but it is possible to define such cut cells, and these cut cells are then only integrated over the specific subdomains. For example, here the skull compartment. All the cut cells in the red compartment would add up skull conductivity to the stiffness matrix, instead of only being, let's say, of one tissue structure. Okay, a summary from Maria Cala's part of my talk. The subtraction approach cures the singularity on the right-hand side of the EEG forward problem. We have, let's say, presented a lot of theory in a SIAM paper in 2007 about the subtraction approach, and in 2009, Florian Drexler improved the integration aspects on the right-hand side, and we even got higher accuracies of the subtraction approach. The full subtraction approach is computationally quite expensive. I do not really use it in practical applications because it has full right-hand sides. It needs, let's say, integration over volumes and surfaces. Very expensive. It needs to do that for every source. We can reduce computational costs by transfer matrix approaches significantly, but still the multiplication of full right-hand sides that have to be integrated and multiplied to the transfer matrix is still computationally expensive. And we are on the way. We have new localized, so-called localized subtraction approaches, where the outcome is the same. The source is also implemented in a fully focal way, but we do it on a smart way in order to reduce the computational effort of the method. We have presented it up to now only in master thesis work, but are working towards a publication for such a localized subtraction approach. The CG-FEM can suffer from skull leakages. Let's say, in EEG, it might be considerable numerical errors that are resulting from it if we use regular hexahedral head models. In MEG, there's nearly no effect that we can see, which is somehow also obvious. So if we combine EEG and MEG, it might be better to do that in a DG-FEM approach. Okay, I said this already. So I think these points are mainly taken care of. And I would now like to let's say, to go over, first of all, to TES and EEG, and to present you these three different worlds to summarize again, let's say, what do we have on the FEM sides, which different approaches do we have, and how much impact does that have before I come to the cut FEM, and which is an unfitted FEM approach. So we are, on the one hand, we could produce a surface-based tetrahedralized head model. Let's say this is standard if we use also BEM approaches. In BEM approaches, the outer skin, the outer skull, and the inner skull is segmented. Surface mesh is produced. The surfaces are not allowed to touch each other. Otherwise, let's say there are theoretical problems. Certain approaches can take care of that, but let's say the general approach might be difficult for skull holes. Same for the tetrahedralized FEM approach. The surfaces, some meshes will not allow that surfaces are touching each other. So in a surface-based tetrahedralized approach, surfaces have to be segmented that have a certain distance to each other. And then the mesher can go on and segment it. And then also geometrically, the surfaces are taken well care of and numerical results are accurate. Then we have a hexahedral mesh. We see already the staircase representation of normally smooth surfaces. So that is truly a disadvantage. But the advantage is that MRI data is available as voxel data. So the segmentation is much easier and much less work has to be put in such models in order to produce a hexahedral model. The best is possibly if we have both information available. We have MRI information, but then we also have level set segmentation results where we know, okay, we now have this cubic structure, but a level set is passing by through these cubes. And let's take that also into account into an unfitted FEM approach so that we combine the two let's say, the two motivations for using these approaches. On the one hand, well taken care of the surfaces due to the level set information. On the other hand, we have voxel information from the MRI. So we bring it together in such an approach. But if we first only look at surface-based tetrahedral approaches, and here the simulation has been run by Nicolas Vogenauer in a recent master thesis study, where we have a stimulation scenario now. So we inject the current at this anode and we extract the current at this cathode. And then we compare the numerically computed potential distribution in this 4-compartment sphere model to the analytical solution. So first of all, this is just the solution, the potential distribution of this stimulation scenario if we look at the overall model. And this is if we only visualize the potential distribution in the brain in the inner compartment. So here we have the relative error between numerical FEM, tetrahedralized CG FEM approach, and the analytical solution on the other hand. So we see that we mainly only have larger errors where the zero potential line is. So 5% relative error where the zero is, we don't care, because let's say if it is 10 to minus 8 or 10 to minus 10, in the application it will not make any difference. More important is possibly what happens around the electrodes. So this is a hint that for the stimulation, more sophisticated electrode models like complete electrode modeling might make sense. Okay, but in any case, what we see here inside the brain, and that is the most important, is, let's say, numerical errors are really fully negligible for that stimulation simulation scenario. The errors are extremely low. So a surface-based tetrahedral FEM or BEM approach is a reasonable approach for such a homogenized scenario. If we now go over to the hexahedral models for the same scenario, and we have 4 mm skull thickness and 2 mm hexahedral meshes, and then on the left-hand side we have a CG, and on the right-hand side we have the DG FEM approach. We already see that errors are much bigger in the hexahedral models, because, let's say, a resolution of 2 mm is just not good. For hexahedra, we should definitely go to 1 mm, otherwise we have significant numerical errors. But what we see also is, in this situation, CG and DG produce the same results, also the same errors. We visually can't distinguish what is better here. So in this case, I would definitely say CG FEM needs less computation. That is the method to go. That is the way to go. But if we now go over to a 2 mm skull thickness in the 4-compartment sphere model, then also for the stimulation scenario, we can work out quite a significant difference between CG FEM and DG FEM. So we see that the DG FEM errors are much lower than the CG FEM errors, relative errors in the brain compartment. So let's say also here on reciprocally, not only for the EEG, but also for the TES, for the transcranial electric stimulation, it makes a difference if we use CG or DG FEM, if the resolution of the model is not good enough to take care of thin compartments that have importance, like the skull compartment, which is low conductive, which is also somehow very logic. Okay, I explained this already. So on the unfitted side, now we are on the EEG side, because here up to there I only had EEG results, but a little bit later on we have a CAT-FEM result for it. So here we have on the x-axis source eccentricity, and we have relative difference measure errors, numerical errors, when comparing the numerical approach to analytical approaches of the MUNC in a sphere model. And we see here that unfitted discontinuous Galerkin shows convergence. So if we go up with the degrees of freedom, we get better and better topographical errors. And if we use high resolution modeling, then we are at 1 or 2% numerical error. So our results are accurately enough for epilepsy diagnosis and other applications. More importantly, the same numerical accuracy can be achieved with UDG with only 39,000 nodes compared with 3 million nodes on the DG side. So this is a 2 mm DG hexahedral model, which produces much larger numerical errors than if we go over and also model, using the level set information, also model better shaped tissue surfaces by cut cell approaches. Then with much less degrees of freedom, we even get higher numerical accuracies. So that motivates an unfitted approach. And therefore, I would like to present to you the CAT-FEM that might be, let's say, an approach that is especially, that we will push especially in future implementations. It is a master thesis that I have just this morning put into the internet. You will find it on my webpage from Tim Erdbrügger, who had the task to implement CAT-FEM for transcranial electric stimulation. Andreas Nüssing, in his doctoral thesis, has already implemented for the EEG forward problem. So let's say what we need in such an approach is, okay, we need, first of all, let's say a head model, an MRI. We need voxel-based information. And we also need, let's say, there's a large bunch of segmentation approaches that use level sets. And level set means that, okay, for example, if I have one hexahedral element here, and let's say if the level set has a positive value here on the green node, and on the two green nodes, in this area it has a positive value 0.5, and here it has a positive value 1, and then the level set information is negative on V3 and negative on V0. From these values, we can derive where the surface is passing by through that phase. So for example, from -1 to 1, linearly, and if we use a multilinear level set, we would know that this surface is passing by in this regular hexahedron on exactly the midpoint between those two. If it is 0.5 and -0.7, then it is about here. So we know where the surface passes by. So in this area here, the level set would have negative values, and here it would have positive values. So we are outside and inside a certain domain. And there might be multiple domains, and we have always outsides and insides that can be produced by segmentation approaches. And in an unfitted FEM approach, the information that is additionally available due to that level set information. So what we need are really these 4 numbers here, or in a 3-dimensional approach, we would have 8 numbers. And by means of these 8 numbers, we would know, okay, let's say we would know where the level set passes that element. A multilinear, let's say in a multilinear level set approach, this would then be what we would model inside the element. So we would produce the cutting points here and here and here and here. And we would model everything that is inside with cut cells that also get skull conductivity. So when the entries to the stiffness matrix are produced, these cut cells would produce the additions to the stiffness matrix with skull conductivity, while these elements here would produce the additions to the stiffness matrix with skin or CSF conductivity, depending on where they are. So even if we compute on a coarse mesh, and even if the basis functions there's only one set of basis functions in that regular element, the cut cells take care that at least the additions to the stiffness matrix, the conductivity of the tissue structure is taken into account. And that makes it very easy to produce an adaptive mesh refinement also, so to make it finer where it is needed, and to make it coarser where, let's say, the resolution is just no longer so important. And I see that time is passing by, so I go over the theory and I just show you a result. So here, on purpose, the surface-based approaches, like, let's say, what is used in FEM and tetrahedralized FEM, does not allow normally that surfaces touch each other. So on purpose, the force sphere is now touching or the CSF compartment is disappearing. So the force sphere is touching the second sphere, while here the distance is larger. So it's unsymmetric. The inner one is unsymmetric and moved on purpose a little bit to the right-hand side to produce a situation where CSF, let's say, patient is lying in the MRI, brain is touching the inner skull, CSF is disappearing, then the surface of the gray matter compartment would be lying on the inner skull, and BEM and FEM and tetrahedralized FEM approaches might have problems because the mesher might say, oh, I can't mesh that. The surfaces have touching points. So this is a scenario that can easily be computed with CAD-FEM. And if we look at the result, and I will directly come to the most important result, let's say if we compare 4-layer CAD-FEM with 4-layer CG-FEM, we see that overall the CAD-FEM result that is much more efficient even, it needs much less computation time, but it is much more accurate because it takes into better takes into account the real underlying geometry. It accepts that level sets are touching each other. So the measure, let's say there's no task to do sophisticated meshing, and the CG measure, first of all, had to be, let's say, trained to produce a mesh for that situation. Many meshers would just say, I can't mesh it because the inner sphere is touching the next one. So let's say with the CAD-FEM approach, it can be modeled easily with high accuracy, and that is what we want. I think, let's say, I still have 15 minutes, huh? Do I still have time to?
Yeah, yes, you have also 10 minutes, 10, 15.
10 minutes,
yeah.
Okay. We can still, say, shortly go to mixed.
Sure, yeah. Thanks.
Let's say one last method, if you're not yet too tired from all these FEM methods, especially the poor BEM people who might have joined. One further approach is the mixed FEM approach. And in the mixed FEM approach, already from the beginning on, a different problem is solved. So this was the problem, the quasi-static approach that we now solved in all of these results that I presented to you. In the derivation, yes, there was one slide where Maria Carla presented that J has been cutted into JP plus JS, and JS was sigma gradient U, the secondary fluxes. So this is now not done. It is, let's say, we even use this equation here. So we write J as JP minus sigma gradient U. So that is, let's say, what we have used in order to derive that differential equation here. Then we use the information that the divergence of J is 0. And we use the information that the normal derivative of J should be identical to the normal derivative of JP on the head surface. And since there are no, let's say, at least in source analysis, there are no sources in the skin compartment, we always have a 0 here. So let's say we have homogeneous boundary conditions for the current density on the surface. And the mixed FEM is now working on this equation system. So let me show you how this works out. First of all, we have now different function spaces in the mixed FEM approach. We need vector valued function space, first of all. So we have the space HDiff, where we have vector valued functions Q, where the divergence of Q is also L2. So that is the HDiff space. H0 diff are those functions Q from HDiff, where the normal derivative, the normal component of Q at the surface is 0. So now we can introduce a weak formulation of these equations too. So let's say if we multiply, first of all, this equation here with sigma minus 1, then we have sigma minus 1j plus gradient, sorry, sigma minus 1j equals sigma minus 1jp minus minus gradient u. And this is what has been done here. Only the minus gradient u, the gradient has been flipped over to the test function, has been brought over to the test function. So it is sigma minus 1j multiplied with a test function integrated. So let's say the standard way of producing a weak formulation, multiplying with a test function, which is now from HDiff space, and integrating over the head domain. This is also done for this part, but only the gradient of u has been moved over to the test function. So it's the divergence of the test functions times u, and then the right-hand side, sigma minus 1jp, comma q, for all test functions from H0 diff. And the second equation here, divergence of j times the test function, which is now a scalar test function from L2 has to be identical to 0. If this is done, then bilinear forms and right-hand side functionals can be formulated. So we have now two bilinear forms, A and B, for the different aspects that have been derived here. And the problem is now that we want to solve 6 by means of finding solutions for the potential U and the current density J, where U is an L2 and J is an H0 diff, so that these two equations are now fulfilled for all test functions. So what the mixed FEM is doing is it does not only produce a solution to the electric potential. In this case here, due to our choice, it's a certain kind of, let's say, DG way, so the potential can jump from element to element. But it also produces directly a solution for the current J. So J and U are unknowns in that approach, which surely means that we throw in far more degrees of freedom. Yeah? That is, let's say, on the disadvantage side. It's a little bit similar to a symmetric BEM approach, or it has certain components that are comparable. So if we do that, then from this bilinear form representation, by means of choosing subspaces, and in Johannes' work in this IEEE paper in 2017, he used constant test functions for the potential U. So let's say U is only assumed to be in L2. It can jump, and he used lowest order Raviat-Thomas elements for the current density. And when doing so, from this weak formulation, we can derive an equation system. So here we have A times J plus B times transpose U is identical to the right-hand side. B times J is identical to 0. And then, let's say, we can use sure complement methodologies to solve it. So Johannes has shown here that when we multiply the upper equation with A minus 1 from both left and right hand side and solve for J, then the upper equation is then J identical to A minus 1 B minus B transpose U. So we can plug that into the second equation in order to derive an overall equation, and that is then called, this matrix is then called the matrix S, or let's say S is then defined as B A minus 1 B transpose, and the matrix S is then called the sure complement. And by solving this, we can directly compute the potential, and then we can use the equations here in order to compute from the or this equation here to compute from the potential also the current. This can be done, let's say, by more sophisticated. We have then inner and outer iterations in the solution process. And preconditioning can be done with algebraic multigrid. That is also shown in this paper. And for the mixed FEM approach, we have similar situations. In order to show where it makes a difference to a standard FEM approach, we can step back to that situation with the skull leakages, and then it is even shown that the mixed FEM is even doing better. It's even alleviating more than the DG FEM, these leakage scenarios. So if we have these cause measures for fine compartments, then using a mixed FEM approach alleviates the problems that are resulting from it. Okay, yeah, he also showed, let's say, results on realistic head models, and he showed that so a very high resolution model was the reference, and the models that come closer to the left side here, so where the RDM errors are, let's say, best possible at 0, and where the cumulative relative frequency is very high, that are the better methods. And he then used 1 millimeter FEM approach, standard FEM approach, that was somehow in this investigation the the method that created the best numerical accuracy because it had the highest resolution. But if we only go for 2 millimeters, then it is obvious that the mixed FEM 2 millimeter approach is much better than the other approaches with regard to numerical errors in that realistic head model. Because in the 2 millimeter model, for the realistic head model, we run into skull leakage problems that we do not have in the 1 millimeter resolution. But let's say if we are restricted due to computational power or something, and we need to go down with the resolution to 2 millimeters, then the mixed FEM is might be here the method of choice, or is let's say producing better results than the standard FEM approach. So let's summarize everything what I have shown to you. BEM approaches in 3-compartment head models are the current standard in EEG and MEG. In TES and TMS, FEM models are the standard. It's interesting. It has historical reasons, I think, why different numerical approaches dominate different areas. It should be said that a 3-compartment FEM model is nearly as good as a 3-compartment BEM model. Let's say the best FEM approaches are always 1 or 2% less good than the best BEM approaches, but they also do a good job on 3-compartment models. What we claim is, in many situations, it is not enough to use a 3-compartment head model, and this will be presented by Maria Carla Piastra in the afternoon, where, let's say, only the adding of the CSF makes already quite a big difference. And this has to be done in order to go for multimodal, or to let's say, to combine EEG and MEG, and to combine SEEG and surface EEG. Then it gets really important that further inhomogeneities and anisotropies have to be taken into account. So I just refer here to Maria Carla's talk. We have different FEM approaches in our software DuNeuro that is openly available to everyone. It has a MATLAB interface and a Python interface. So this is the way how we merge it with openly available toolboxes like Fieldtrip and Brainstorm and MNE Python and such tools. And for us, it is just instructive to have these different possibilities. Mixed FEM is not yet implemented. It's on the way to be implemented, but DGFEM and CGFEM and UDG FEM, so unfitted FEM, is implemented, and you can play with it and compare. And what is better is always depending on the situation. Fitted and unfitted FEM show accurate results. Their choice should mainly depend on the mesh properties. So the most important is, if you do not have level sets, you cannot use unfitted FEM because it needs this input information. So if you only have voxel segmented MRI, then you have no choice to use CG or DG or mixed FEM on that hexahedralized head model. If you have a surface-based approach, like let's say in the 3-compartment BEM approaches, then you can go for all different kinds of FEM modeling also. While mixed FEM and DG FEM are current preserving, CG FEM is not, but this seems only relevant if thin compartments with considerably different conductivities have to be modeled with limited resolution. So we always, let's say, used a very thin skull compartment in order to visualize the differences between those approaches. That is possibly the situation with where we can tweak it out where the main differences happen. We want to go for unfitted FEM in the future because, let's say, level set information is available. And then still, we do not need sophisticated meshing approaches. So let's say, this CutFEM approach showed less deviations in the 3-layer, 4-layer test case, and that is a difficult test case because surface-based approaches like BEM and FEM have difficulties if spheres touch each other. So the meshing tools might already break and they not produce any result. And if we have level set information, the CutFEM just takes that information. It will not break. It will produce a numerical result. And it is just much, let's say, it's facilitating the modeling of touching surfaces, which really happens if a subject is lying in the MRI. The inner skull and the brain surfaces are touching each other or lying on each other. So it might facilitate mesh generation and forward modeling of such situations. CAD-FEM outperformed CG-FEM in most categories on the electric side. We have not yet tested it on the MEG side. It's not yet implemented, so we need to do that. It needs much less degrees of freedom and therefore less memory. However, it is surely far more expensive for metric setup because it has to integrate all these surface jumping potentials on the surfaces, all these Nietzsche terms and the penalty terms. So the matrix construction is much more expensive. However, this has to be done only once, and then in combination with the transfer matrices, we can make it very fast. Okay, that's it. Just to advertise an epilepsy project that is now starting in summer. So we want to use combined EEG and MEG source analysis to find the epileptogenic zone in the brain of focal epilepsy patients. So that couples my talk to Lino Nobilis' great talk this morning. We want to, let's say, use this information for SEEG, for radiofrequency thermocoagulation, in case that surgery can be done. But we also want to use that localization information to optimally target brain stimulation with multiple channels, so multi-electrode transcranial direct current stimulation, in order to try to reduce number of seizures and severity of seizures in a certain kind of practically non-invasive way, just by non-invasive brain stimulation from the outside. And we want to do that in combination with Fabrice Valois on epileptic children, and evaluate, let's say, how much the combination of EEG and MEG can, for example, contribute to it, how much the different FEM approaches can contribute to it, the optimization approaches can contribute to it. So this is a big project where we try to make use of these sophisticated software developments in neuro in order to bring it into into clinical applications and help severely ill epilepsy patients. And thanks a lot, especially, let's say 80% of my talk slides were from Maria Carla Piastra, who is shown here. Andreas Nüsing has done a lot of the work for neuro. He has developed the CAD-FEM for EEG. He has also, let's say, pointed out, or let's say he has also implemented the main basic part of neuro. So one of the most important developers of neuro. And then I would also like to mention shortly Johannes Vorwerk, who has implemented the mixed FEM and who has also compared DG and CG FEM approaches in EEG situations. And that's it. So I have filled the 2 hours, my longest talk on the conference ever. And I hope you are not all sleeping.
No. Thanks a lot, Carsten. It was very interesting, and you gave a lot of useful information for people working on the forward aspect, but also for people working as me in inverse methods. So thanks a lot.
Thank you very much.
Yeah, so I see if...
Should I stop sharing my screen?
Yes,
and we can
okay, thanks.
Possibly. So are there questions, or is there still time for discussion?
Yes, I think we can reserve some 5 minutes more to discussion. Is there some question? I check the chat, or you can raise also the hand. Okay, Alberto. It's okay.
A tough mathematical question comes.
No, there is. I think I've seen Alberto raising the hand, or not?
Alberto Valli.
Do it, or?
Oh, okay.
Can you do it, Annalisa? I can't.
Yes, I think it's so. There is, okay, Alberto Valli. Okay, now
Yes.
it's on me.
Thank you. So just a very simple question. Thank you, Carsten, for your wonderful talk. It was really wide and deep, so thank you. And I was just curious about the choice of the elements. That is, you spoke about hexahedral elements and tetrahedral elements, and in some situations, for instance, for skull leakage, you have told us that the tetrahedral meshes are better in some sense, that you have not that phenomenon. And so why not working on that type of mesh every time in some sense?
Yeah. Let's say the answer is very simple. To produce a 5-compartment, let's say, what does a tetrahedralized approach need? It needs 5 surfaces. Or let's start simply. The standard is nowadays that people produce surfaces of outer skin, outer skull, and inner skull. Yeah, and then they go for a BEM approach. That is, let's say, what Curry commercial software is doing on button press. What they always try to do is they keep the surfaces away from each other, because if the surfaces touch each other, there are lots of problems. Yeah, there are mathematical. You can treat it numerically. There are also BEM approaches that can like fast multiple methods from Sergei Makarov, for example, and other developments that can model holes. But modeling holes with a BEM approach is already very sophisticated, and standard BEM approaches can't do it. And also on the FEM side, a tetrahedralization tool like TETGen or NetGen, so good meshing tools where people have invested 10 years to produce high quality tetrahedra. Those software tools very often just give up if the surfaces are touching each other. Then the software might tell you, I can't mesh it because the surfaces are touching each other. That is a situation that I cannot make sure that the conditions for good mesh properties are fulfilled. And then those meshing tools stop producing a mesh. So now we are in Münster, we are speaking no longer about 3 compartments. Our main work is, let's say, or what I say to my colleagues out in the world is that 3 compartments is quite homogenized. It is, let's say, nobody believes that the human head is just consisting of 3 blocks of tissue. It's just very homogenized, and it's much more complicated. And when you ever work on a data set of stereo EEG combined with EEG, then you know that this is far away from the real volume conduction. So then you have to go up. At least you have to include CSF. You have to include gray-white matter distinctions. You might have to include anisotropies depending on where your depth electrode is. And already when you combine EEG and MEG, you are running into that trouble. That 3 compartment homogenizations are really, let's say, outdated, I would say. Yeah? The brain stimulation people, their standard is a 5 compartment or 6 compartment model. Everyone uses 5, 6 compartment FEM approaches in brain stimulation. I don't know why. Yeah? It might be because of the definition of the mathematical point dipole in source analysis, because the combination of homogenizing in the source area very strongly with 1 brain compartment where the source singularity is somewhere in the middle, that is just, let's say, relaxing the difficulties of the numerics a lot, so that the combination of 3 compartment modeling and BEM and the mathematical point dipole is reasonable. Yeah, I also use these approaches depending on the task, and it's not wrong, but it's on the other side also far away from let's say reality, from a human head. So coming back to the question, let's say it is a difficult task to produce for 5 surfaces, first of all surfaces are not allowed to touch each other. Try to segment white and gray matter, and both surfaces are not allowed to touch each other. You need really good methods. FreeSurfer is doing that reasonably well, and you can keep the surfaces away from each other. But in reality, when I'm lying in the MRI, my brain is lying on the inner skull. I can show you my brain. It is plotted in 3D, and you see how flat my cortex is. Yeah. So I'm lying on the inner skull. It's compressed. Yeah. So the tetrahedralized approach, let's say segmenting such a surface is the brain surface is lying on the inner skull surface. And then NetGen, TETGen, all these approaches will just give up and tell you, oh, I can't mesh that. And then let's say you're lost. As someone from application, you're lost because the mesh is not produced, and then you cannot do forward modeling, and then you cannot do source analysis. So in this situation, hexahedral models are much easier to produce. In hexahedral models, there are no distances that have to, let's say the brain can just touch the inner skull. There might be a hexahedron from the brain that touches the skull, no problem. All these restrictions for well-shaped tetrahedra are no longer there in a hexahedral head model. But you're running into these troubles, especially for coarse resolutions that we have shown. The skull leakages and let's say the surfaces are not smooth. My surface is truly very smooth from, let's say, from the cortex, from the inner and outer skull, that are all very smooth surfaces, not staircase-like. So therefore, I think the future is the level set approach. Segmentation approaches have no problems to produce level sets, and level sets can touch each other. And the CAD-FEM is just easily embedding it, making no trouble in deformed elements. Yeah? Since the CAD cells are only for integration purposes, they are not adding degrees of freedom to the problem. They are only adding more accurate integration information to the stiffness matrix. That's much easier to generate. So I think this is a future, but it's sophisticated. The software is sophisticated. We have to test it. We have to implement it for MEG also. It's only available now for EEG and TES. But I think this might be something that really DuNeuro can offer to the community. Let's say to have the possibility to, if you have a tetrahedralized head model, then go for the conforming tetrahedral FEM approach. That is the way to go. Just a Lagrange approach, best method. If you don't have that, and you really want to model a lying brain on the inner skull, then you have to make more efforts in the segmentation. And then there are these other approaches available that could be used.
Okay, thank you.
Thanks. Is there other questions?
I see the hand of Andreas Ioannidis from Cyprus.
Okay.
But I can't hear you, Andreas.
Yes, I try to
unmute.
Yes.
Okay. Wonderful talk, really enjoyable, especially for somebody who is not an expert in this field. But a lot of the discussion, the response to the last question, brings another very important problem. If we are modeling the head as it is in the MRI scanner, we are not in that position going to do a real experiment.
Yes, so the epilepsy patients are lying.
In the epilepsy patients, but if we're going to do modeling or EEG or MEG study that we're sitting and we don't have this pressure, then we're looking at a different model. Could we correct that by expanding this volume? Because I assume that the modeling errors would be much higher because of this distortion.
Yeah, so first of all, to point out clearly, our epilepsy patients, they are lying in combined EEG-MEG investigations, and they are lying in the MRI because we want to do that accurately. And there is this paper of Rice et al., Neuroimage 2011, where it is shown that this CSF that is compressed has so much effect that the EEG is reduced by 80% if the CSF is compressed or not. So they have worked it out experimentally how important the CSF is in that area. So I think it is practically, it has been shown to have practical importance to do it. But I understand your question, because the most MEG studies are done in sitting positioning, especially if the subjects have tasks, because then if they have tasks and they are lying, they get tired and they are less good in performing the task. So the sitting position is important. And I think it was your idea now that we somehow use the information that we have in order to take those errors into account from the lying MRI positioning to the sitting MEG positioning. And it is similar to, let's say, in epilepsy, how is it called, where the brain is moving due to opening the skull, the brain shift, or is it brain shift? In any case, let's say what we would need is a nonlinear registration of the lying to the sitting situation. The problem is a little bit, there is no MRI in the world where we could get an image of the sitting situation. So we would have to estimate it. We could, let's say, move the brain in the volume, let's say in the head model, a centimeter to the front in order to simulate that the subject is sitting and not lying, but it's also a simplification. Yeah. So let's say, very difficult question, and in my experiments, everyone is lying, yeah, because let's say we want to go for this, and I do not want to get from the reviewer the question that, haha, you did so much effort and then the subject is sitting in the MEG. But in other work groups, subjects are mainly sitting. I know that surely. And if I do first tests with students, they are also sitting, also in my group. So that, let's say, then we have to be aware that the setup of the head model is limited in the quality, or we have to model the lying situation produced head model using nonlinear registration in order to make a sitting head model out of it, which could be done. Yeah, I think it is. Yeah, we can't hear you.
No, why? We can't hear. No.
I can't.
No, we can't hear.
Andreas, you have to unmute yourself.
But I think we have to do it, Annalisa, but
Yeah.
I'm not able.
Okay.
Can you hear me now?
Yes.
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 Okay, you have to unmute me from that end. Yes, I agree with everything that you said, Carsten, but there is a solution. You cannot have an MRI in the sitting position, but you can have an MEG in both conditions. In fact, we did something like that, not doing any finite element models or anything like that, but just by trying to approximate that, by having the same subjects do a sleep experiment in which they have in the same location, and then using the same subjects for an evoke response and modifying their brain to fit what we had from the other one. But it's not easy, and there's no way of validating it. But I think it's something that the community, I mean, given all the effort that you are putting for these wonderful models that we would love to use for evoke responses, it's a feasible approach. It can be done, especially if we can, from a given brain, we can actually predict from the shape and from what we see on the MRI, the amount of distortion. I think it's a difficult problem, but it's a solvable problem.
Yeah, absolutely.
Thank you very much. It was really,
you know
really
the Rice
nice.
paper? Do you know the paper of Rice et al.? So what they have done is they've produced visually evoked potentials in supine and prone positioning. So one time the subject was lying on the back, next time the subject was lying on the stomach. So the two extreme situations for the occipital area, and they have shown, and they have done the same in MRI. Yeah, you can do an MRI while sitting on the while lying on the stomach. It's possibly not comfortable, but they have done it, and they have worked out that the CSF compartment is then something like 2 millimeters thicker in stomach positioning compared to back positioning. And these 2 millimeters made up 80% amplitude in the evoked potential, in the visually evoked potential. It's a great paper. I spoke with Scott McCaig about it and this group, and no, it was Don Tucker. And Don Tucker told me it's a great paper, but we tried to redo it, and we could not replicate it. So I think, let's say, it is interesting, and we should do more of these studies. Let's say for this problem, it is now very interesting to go from sitting to lying and to see what are the differences, how much does the brain move, how can we best embed that in head models, how can we still profit from better head models that also take that into account, this brain shift, yeah, this shift from sitting to lying. Absolutely right. So one good reason to homogenize the inner part, yeah, let's say if we have sitting position MEG and lying position MRI, what we can do is 3 compartment head modeling, and then we are back to what people are doing very often.
Well,
thank you.
Thanks a lot, Andrea. And thanks a lot to Carsten again. If someone has other questions to Carsten, can also write to the chat or to use the room. So I don't see you more. Okay, Carsten. Okay.
Thank you very much.
Thanks a lot again for
Thanks
this.
Thanks a lot also for inviting me for this very long talk.
Yes, but it was very interesting. I got a lot of important information, and we thank for accepting our invitation.
Thank you very much.
Thanks a lot.
Good lunch.
Grazie. Good lunch to all, and we start again at 2:30.